Good afternoon, everyone. I'm quite aware I'm between you and your lunch, so I won't be keeping you.
You are from University of Chicago, right?
That's right.
Yes,
Yeah.
sorry, that was my mistake.
Yeah.
US, yes.
Yes. So I work with University of Chicago. They have a center in Delhi, and I am one of the people in the field. We work with different governments on river water pollution monitoring projects in India. My talk today is titled A Water to Cloud Approach Using Cyber Physical Sensing Network. I'm going to talk about mapping and monitoring of large water bodies such as rivers and lakes using mobile sensors as opposed to the traditional approach of just collecting grab samples. To give you some context, India has about 16% of the world's population, but less than 4% of global water access. And hence, conserving water and then doing something with the wastewater being generated in the country is more important for India than other countries. It's not unknown that about 80% of the sewage in developing countries, according to 2015 UN report, goes untreated into seas and oceans. And a lot of these Indian rivers, especially, are polluted with fecal matter, agricultural waste, industrial waste, and all of that has effect on human health as well as the ecology. As I said, the traditional approach of water quality testing, which is often the main approach used by the Central Pollution Control Board, the central nodal agency in India, to monitor water bodies, is to collect a sample of water from a specific place, take it to the lab, test it, tabulate the results, leave it in a report. Oftentimes, no one actually reads these reports for years. And so some of the gaps in this traditional approach involve the usage of the actual data collected, but also whether the methodology of that data collection was appropriate, whether you're actually able to get right insights out of that data. Because collecting one data point from a city like Varanasi in India or like Delhi in India over a period of 1 month does not actually give you any information about the level of water pollution in that area. It could be a data point just before an industry or after an industry, before a major drain or after a major drain, and that actually completely changes the picture. And hence, because of that, it's actually oftentimes not even used for any public policy discussions. The approach that we're talking about is where you identify the parameters of importance for your study. So oftentimes we work with our stakeholders, which is the government in this case, and identify whether in a particular area they want to concentrate on industrial waste, or if it's a huge urban center, then mostly it's going to be a lot of domestic sewage that's going to come into the picture. So once you have identified those parameters of importance, we look at so we look at the right sensors available in the market to then go and monitor those parameters, and I'll come to the specific parameters in a minute. Once we have those sensors, the method that we use is these sensors are automated sensors. They have a geotag and time and date stamp capability along with measuring the parameter. These sensors are attached to a boat. They have handheld meters which record the readings which are kept on the boat, and we choose a path, which is the map that's shown here. This is Rajamundry in Andhra Pradesh. This is the river Godavari, and we choose a path and we go zigzag across the river. So essentially we scan an entire area instead of just taking one point. These automated measurements happen every 1 second or 5 seconds based on how you tune it. And once you come back on land, you upload this data to the cloud network. So when you upload the data to the cloud network, you have a CSV file or an Excel file. And oftentimes, this is how the government's data in India remains, which is quite a non-user-friendly approach to interpret the data. Because this data is geotagged, we put it down, we superimpose it on Google Maps, and then try and interpolate the data to get an entire scan of the river. So it essentially helps you look at spatial variation of the parameter. All of this is available on our platform for anyone to download in the form of raw data as well as the interpreted heat maps. So the parameters that I was talking about, we look at a number of physical, chemical parameters, the simpler ones being pH, temperature, dissolved oxygen being an important parameter to look at events like fish kills in rivers, turbidity telling you about a lot of human activity in the area, and a bunch of other parameters, which is the fluorometric sensor there, which looks at CDOM fluorescence, which looks at tryptophan fluorescence, chlorophyll values, and these are optical parameters, but they talk a lot about the overall health of the river. CDOM and tryptophan in particular have been found to correlate with levels of BOD and fecal coliform in the river. If most of you would know that BOD takes 5 days to test in the lab, fecal coliform is also a difficult test to perform in the lab, and these are quite expensive tests in the lab. Here we have a sensor that can actually get us values which can be correlated with these two parameters, and these sensors can get measurements every 1 second instead of waiting for 5 days. A bunch of parameters we still need to test in the lab because oftentimes sensors are not available or they're not reliable. And then along with all of this, we take measurements using a flow probe to estimate the quantum of wastewater entering the river. So while it's not just important to say what is the concentration of BOD in the river or just at the mouth of a drain, or the concentration of electrical conductivity, but also the amount of those ions that are entering into the river. These are some of the places across the country where we have been doing a study for the last 2 years. This is just a pictorial representation of how the sensor probe goes into the river. There's a meter there, the cloud network stores the data, and then it's available on the website. Some pictures of our field team. These are the probes that go into the water, and these are the meters that record the data. There's a picture from Yamuna in Delhi, not too far away from here actually, and that's the dire condition of the river. This is a picture of a factory, a paper mill in fact, in Rajamundry in Godavari, and I'll go to the results in a bit. So as you can see the key features of this approach are twofold. One is to be able to temporally and spatially map the water body in terms of the specific parameters of interest. So these figures here show electrical conductivity measurements in Godavari at Rajamundry, and these are measurements from different dates, and the boat was taken around this area. So while you can see a variation in the color on a particular day, you can also observe it between days. So it's also temporal as well as spatial. On the same principle, actually, you are then able to identify specific sources of pollutants entering the water body. For example, this is Varanasi, in Ganga in Varanasi, and there's a major drain here, which is why the dissolved oxygen levels are going much lower than other places. Sewage waste is often contaminated with fecal waste, and a lot of so the dissolved oxygen levels would be almost zero around that area. These GIFs will actually help us understand this better, where if you look at the electrical conductivity in Delhi, in Yamuna, you can see that over the 3 or 4 dates that I've been rotating these pictures here, a lot of blue water is seen on the initial day, which is a low electrical conductivity because of the fresh water being released. And then by the 3rd or the 4th day, it's almost yellow, which is a full mixing of the drain water and the fresh river water. Looking at some of the results, something like this can be used to be able to can be used as an aid for regulatory compliance. We've been speaking with Niti Aayog in India and Central Pollution Control Board, and they're quite happy to look at this method to then be able to get a comprehensive picture of where exactly the industrial waste is entering. For example, this paper mill in Andhra Pradesh has been releasing a lot of waste in the middle of the night. Usually the government measurements happen at 2 p.m. and that often just misses out the point of the amount of waste that's going into the water. But with this method, if we take measurements at early morning, evening hours, then we can actually point out what is happening. Yeah, another important bit with rivers being considered very holy in this country is finding safer ghats for people to take a bath. About 20 lakh people or 2 million people in India on a daily basis take a bath, take a holy dip in the river Ganges. And for them to be able to identify which ghat areas do not have high level of fecal contamination is very important for them to then go and take a dip. So tryptophan values, as I said, can be correlated with fecal values, and that may help them doing that. Supporting authorities with water management. In Delhi, what is happening is the Delhi government releases fresh water very randomly. As I said, by the 4th or 5th day, the mixing of the drain water with the fresh water contaminates it so much that it's a health hazard. So if they have this information, the exact amount of time they need to start releasing the fresh water again, it may help them with better management. Quantitatively estimating pollution load. Again, as I said, because we take the flow measurements, which is something that even CPCB in this country does not record, we are able to see how much of the waste from this drain is entering the river. And that can help with the quantification of the pollution. To give you some statistics based on our initial results, as we can see, most of the rivers have a very low dissolved oxygen. So dissolved oxygen should be above 5 for bathing water standards, but often rivers in India have much lower dissolved oxygen. BOD similarly should be less than 3 milligram per liter, but oftentimes you see that the values are much higher. We have been using some machine learning tools to do predictive analysis on these data sets we have been collecting. But this is the first time when you actually moved away from just taking one data point at a place to taking hundreds and thousands of data points in the same place. So we wanted to see if we can use machine learning to then target parameters that we are not able to measure online or in real time. For example, BOD. Can BOD be estimated using a bunch of parameters such as dissolved oxygen, electrical conductivity, pH, temperature, and a combination of these using machine learning models to give us an estimate of BOD. And this is a correlation matrix that we use initially. These are some of the results for COD, and we have similar thing for BOD. However, as you can see, we haven't been very successful so far, but that's because a lot more data needs to be coming in before we can get this going. The overall idea and the vision that we have is to then be able to, similar to a geopixel, then be able to have all these layers of data in the vertical form superimposed on each other using government data, using health indicators, and then combining all of this to then give you a picture of what interventions are relevant to this place. Some of the United Nations Sustainable Development Goals that we've been trying to address through this work are presented here. Obviously, clean water and sanitation and health being the major ones, but also trying to make cities sustainable and looking at events for fish kill. And yeah, that's it. Thank you.
Thanks a lot.